So often when I am being asked to give some motivational lectures to much younger students, maybe high school students, I often ask the students this following question. Suppose you have 2 crates of fruit, 2 crates, and there are fruits here. So one consists of say apples, or say one, okay, these are say oranges. So here you have oranges, and in the other you have apples. And so on. Don't take the drawing so seriously. So here are apples. Now so this is crate 1 and this is the crate 2. Which one has more fruits, crate 1 or crate 2? Here obviously from the drawing it is clear. But suppose you do not know to count, you have no idea about the numbers 1, 2, 3, 4. How do you know which has more fruits and which has lesser fruits? Whether you have more oranges than apple or apples than oranges, or are they equal? So usually when I ask this question, the usual reply is that okay, we'll weigh these 2 crates. But you know, with very different amount of apples and oranges, the crates can weigh same, right? And with equal number of apples and oranges, the crates can weigh different. This is basic physics, because you really do not have to, the numbers really don't have to be counted when you are looking for weights. So now the question is, what would you do? Sometimes some students come up with the real answer, and that is exactly what counting is. That you take an orange from here and take an apple from here, put them, club them together and keep them aside. The same, you continue doing it. Suppose after, when you see that okay, I finished in the crate 2, there are no more apples, but there are oranges still left, so oranges are more. But if the reverse happens, then the apples are more. And or you see both of the crates are empty at the same time, then you have the same number of apples and oranges. So this process of corresponding one object with the other is exactly the method of counting. In the earlier days when numbers weren't there, shepherds used to apply this methodology. So when they would send their flock of sheep, they would for each sheep that's going out, they will take a stone and put in a bag. Now when the sheep come back, so what they will do, that for each sheep coming in, they will take the stone out from the bag and throw it. If all the stones finally exhaust from the bag, then all the sheep have come in. If some stones have remained, some sheep have not come in or eaten by wolves or something has happened to them. So this method of one-to-one correspondence is exactly what counting is all about. What these numbers 1, 2, 3, 4 did is that they made a basic set by which you can do all those correspondence. So let us now talk about a countable set. So countable set is a set whose elements can be put in one-to-one correspondence with the set of natural numbers. So a set M is countable if its elements can be put in one-to-one correspondence with N. With a set of natural numbers. So, if M consists of elements and so on, it could be a finite set, it could be infinite set, I am keeping that open. then the set of natural numbers is this. Then this is the correspondence. So A1 is the first element, A2 is the second element, A3 is the third element, and so on. This whole process of one-to-one correspondence, if you have learnt in high school, is actually a way of creating a function. So essentially what we have done, we have created a function from the number n to the set M. So this is a very abstract function, but if this A1 into A3 are real numbers, then we will call such a function as a sequence. So if I have a very specific scenario where M is a subset of, say, R, so M, where M is subset of R, then M is the range of the sequence function. So this function is then called a sequence function. So I have not spoken about functions literally doing the definitions, but I expect that since you have already are in the high school and above, so you would have some idea of what functions are. So this whole procedure is a one-to-one function. Similarly, there can the inverse function is a one-to-one function. The f inverse is from n to m. So A1, f of A1 would map to 1, f of A2 would map to 2, and so on and so forth. There are very strange things. If you have a subset, say you have 10 elements. Now if you make a subset of 5 elements, you naturally know that the subset has less number of elements than the whole set. But this may not be true when you have infinite sets. So infinite sets, there is a very strange way of looking at things. We will come to that very soon. So this is the method of counting, this one-to-one correspondence. This method of counting says one very simple fact, that if M is a countable set, then so is M union X. How does one prove this fact that if M is a countable set, then M union X is also a countable set? That is, if you add one element, it doesn't affect the basic countability. So here I will give an analogy of a hotel. It is called the Hilbert's Hotel, and this hotel business would actually solve all the problems that you will see coming. All your answers will come from the hotel business, right? So it's a nice stuff. Many of the good books speak about it, not all. Standard books don't. I do not know why. Sorry. Hilbert's Hotel. For those who do not know, David Hilbert was one of the greatest mathematicians of the late 19th and early 20th century. A very big German mathematician. Hilbert's Hotel. So there is this strange hotel, say beside a nice hotel. This is the balcony sort of thing, and here are the rooms. It's a very strange hotel. It's an infinite hotel. And then, so this is room number 1, this is room number 2, room number 3, room 5, 4, 6, and so on. Now suppose all these rooms are now filled. And then another guest arrives, who is supposed to be a mathematics teacher, and he says that he wants a room. The manager says, "Oh, sorry, we are completely booked." He says, "Don't worry, just shift the person in room 1 to room 2, room 2 to room 3, room 3 to room 4, room 5 to room 6, and so on, so that room 1 would become empty for me." So he is that X. Right. So which means that these persons the persons who are occupying these rooms were actually elements of the set M, and this new guy who comes in is the set X. So, this is the simple criteria which solves many problems. So, Galileo observed, for example, this very strange phenomena about the infinite world, which is this, that if you take the set of odd numbers, which is 2, 4, 6, 8 and so on, and a set of even numbers 1, 3, 5. Oh, sorry, I am making a mistake. The set of odd numbers 1, 3, 5 dot dot, set of even numbers are 2, 4, 6, 8. So, now these are subsets of n. So, suppose I take this set O, the odd and the even. So, you can have the odd numbers as 1, 3, 5, 7 and so forth. The set of even numbers are 2, 4, 6, 8 and so forth. So, you might think that these are subsets of n, both O and E, these are proper subsets of n. Now, you might say that okay, they should contain less number of elements, which looks very fair by the standard judgment because our minds are very finite, but they are not. There are as many odd numbers as are there as many natural numbers. The same, the number of even numbers is essentially same as the number of natural numbers. There is no such thing like even number is less and odd number is more. There are some sort of cardinality, if you call it infinite cardinality, that cardinality they are same. So, there are as many odd numbers as there are natural numbers, as many even numbers as there are natural numbers. So, for example, so I take the odd one, 1, 1, 3, 5, 7, 9 and so on, 11, 13. And so, the natural number set, so how do I do it? 1 is related to 1, 3 is the second odd number, 5 is the third odd number, 7 is the fourth odd number, 9 is the fifth odd number and so on. So, here I have been able to set up a correspondence. So, once I have set up this correspondence means you are done. So, there are as many odd numbers are there, the number of odd numbers, there are as many odds as there are numbers. So, this is a strange way of behaving of the infinite world. Now, what about this z, set of integers? Of course, this is countable. So, how do you prove its countability? Just apply the Hilbert's-Hotel principle. So, simply once you have n, which means if n is obviously countable, so n union 0 is countable. So, this is a countable set. So, n union minus 1 is countable and so on. This Hilbert-Hotel principle will actually prove the countability of all those things. So, z is countable. So, z is a so set of natural numbers is countable. Set of natural numbers is countable. Set of integers are countable. Now comes the set of rational numbers. So, we have spoken about rational numbers, irrational numbers. We will discuss irrational numbers in detail in the next class, but here we are talking about the countability. You might ask why you are bothering about your countability and uncountability and what great things that they would do. But this method of proving countability and uncountability, for example, has huge implications in computer science. So, you will learn later when you will talk about Turing machines and all those things that these methods are very this we will soon come to a method which is extremely powerful. So, now we are going to speak about the countability of the rationals, that rational numbers are also countable. Remember, rational numbers are dense in the sense that if you take any real number and take an open interval around it, then you will always get a rational number there. Same with irrational numbers, but still the rational numbers are countable in the sense that we have just told that we can put them in one-to-one correspondence with that of the set of natural numbers. So, Here is one of the major theorems of mathematics, of whole mathematics actually. Q is countable. So how do you prove it? The proof is done by a simple diagram actually. And this whole idea of proving was due to a man called George Cantor. When we write this name George Cantor, or we just mention it, we hardly know the perils or the struggle this man had, this great mathematician had. So when we tell that this thing was done by this person, one might feel that okay, he was just having possibly coffee in CCD or some coffee day or barista or some place, and he just wrote something. This sort of attitude we would like to take nowadays, but it is far from truth. George Cantor, a very brilliant mathematician, whose supervisor was Leopold Kronecker. He couldn't get him a job in Berlin. He did his PhD in Berlin. So because he couldn't get him a job in Berlin, he gave him a job in at that time a more mid-sized university in Halle. And in there, Cantor, for the first time in his life, took infinity head on. He asked this question that I would assign some infinite cardinality to some symbol to the cardinality of this set n, the set of natural numbers. And he wrote this as the first letter of the Hebrew alphabet called Aleph, Aleph naught. This is called Aleph naught. So it's called Aleph naught. So this, and he said that any set which can be put in one-to-one correspondence with the set of natural number, that is any countable set, has the same cardinality. Now this was an attempt to classify infinity itself, a thing which Kronecker never liked. And so Kronecker, he and his whole gang had not allowed him to publish any of his ideas. We will soon prove one of his greatest ideas, that the set of all real numbers is not countable. You cannot put them in one-to-one correspondence with the real line, with the set of natural numbers. So obviously then infinity is categorized, something is countable and something is not. This countability and uncountability, the terms might look very simple English words, but in them lies a very deep fact about mathematics. You are essentially classifying infinity. So that is what Kronecker never liked, and as a result of which Kronecker and his chelas, I would say, who had actually put George Cantor into huge trouble. He was hugely mentally stressed to the extent that he couldn't publish anything in Germany. His friend from Sweden, Mittag Leffler, actually allowed publication in his journal called Acta Mathematica. So now, I have visited Halle many times. I have seen George Cantor's handwriting. He is writing to Weierstrass, trying to write to Kronecker to convince his teacher that no, what he is thinking is correct. Only David Hilbert later realized that what he did was great, and then in the 1900, the Second International Congress of Mathematicians, Hilbert had made this very famous statement: "Let no one evict us from the paradise which Herr Cantor has created for us." So, the George Cantor used to be treated so badly, he got so mentally affected that people would come, when he would take a class, people would come and speak so badly with him that he would sometimes faint inside the classroom. They would enter the class and speak in languages. They would come from Berlin, do this to him and go away. And they were all fan followings of his teacher Kronecker. But ultimately, Cantor's work remained to be the one which people use till date. Without these things, mathematics won't be what mathematics is today. So let us look at this counting business. So I am arranging the rationals. What I am doing is this. So I am taking the number 1, then I am writing 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by whatever you want in equivalent. Similarly, take the number 2 and 2 by 1, 2 by 2, 2 by 3. You can say, okay, you have repeated 1 because 1 by 1 is same as 2 by 2. Okay, that doesn't matter, but 2 by 3, 2 by 4, 2 by 5, 2 by 6, 2 by 7 and so on. So, just let me write down 3 by 1, 3 by 2, 3 by 3, you see again 1 is repeated. 3 by 4, 3 by 5, 3 by 6, 3 by 7, 4 by 1, 4 by 2, 4 by 3. So this is all dot 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 dot. Ultimately it just goes on. 4 by 4, 1 is repeated, 2 is repeated here. 4 by 5, 4 by 6, 4 by 7 and so on. So let me see how would I start doing this job. So let me take the first number, P by Q. So what you sum these two. What is 1 plus 1 is 2. Are there any P by Qs where the sum of P plus Q is 2? No. So you first start with this scenario. So P by Q with P plus Q equal to 1 is this one. So start from here. Now look for the cases where P by Q where P plus Q is equal to 2. P by 2, so this is 3. P by Q is 3. Obviously we have taken off 0 out. 0 is just like this Hilbert Hotel, we can just put in 0, no problem. We start with 1 and the next stoppage is 2 by 1. So I come and take this as the next element and from there I start 1, 2 and then 1 by 2 also makes 3. So I go here. Then I have to look for P by Q. This is the way the table is created. P plus Q equal to 4. So what makes 4? 1 plus 3 makes 4. I go there. Next count. Then I come down. 2 by 2 makes 4. 3 by 1 makes 4 and nothing else makes 4. So now I am again looking for P by Q is equal to P plus Q is equal to 5. So what is the next number which is making 5? 4 by 1. So 4 by, I come to 4 by 1. So after 4 by 1, 3 by 2 makes 5, 2 by 3 makes 5, 1 plus 4 makes 5. So then again I do the job. Is 6. With what number makes 6? 1 by 5 makes 6. 1 plus 5 is 6. So you come here and what makes 6? 2 by 4, 3 by 3 and 4 by 2. Then what number makes 7? 4 plus 3 makes 7. 3 plus 4 makes 7. 2 by 5 makes 7. 6 plus 4 makes 7. Then is 8. What makes 8? 7 plus 1 makes 8. 2 by 6 makes 8. 3 by 5 makes 8, 4 plus 4 makes 8 and again 9 and you just go up. So you see how simple this idea of counting is. Now nobody could come up with a pattern. Of course it doesn't matter if you count a number twice. Basically if you throw away a countable number of quantities from a countable set, you again have a countable set, right? So if you throw away those, you still have it. So now nobody could come up, even in the early 20th century, a way to evaluate the rationals so that I do not take in any rational which is not in the lowest form. So every rational appears once. So this is that result is very recent. It is called the Caliph-Wilkin theorem, which you will see in the notes, but I will not discuss it here. So it's quite a recent result. They show you how to do it using trees and all those things. Now, did I really prove Q is countable? No. By this diagram, what I am proving is that the set of all positive rational numbers is countable. So basically, in some sense I have proved here. So what about the negative rational numbers? You have to put a negative in front of them. So you take again the Hilbert's hotel principle, put 0 in, then put -1, then put -12, keep on doing. So each one of them would again be countable. So the whole set of rational numbers Q is countable. Once that is done, I come to today's last and extremely important idea. The idea is the following, that the set of real numbers unfortunately is not countable. You cannot put the set of real numbers in one-to-one correspondence with the set of natural numbers. So this result was published by Cantor in 1874. So it is uncountability of the rationals. Yeah, of the irrationals or uncountability of the reals. The set of real numbers are uncountable. And in doing so, he introduced the famous diagonal method of Cantor, which you will see in detail in the note. Now, if you take a countable set and take a subset of that countable set, what do you expect that countable set to be? What do you expect that subset to be? Either it is finite or it is countable. So if a subset of a given set is not countable, then the whole set cannot be countable. This is a simple fact of logic we keep on using in our daily lives. This works very well actually. A lot of mathematical proofs can be handled in this method. So if I want to prove P implies Q, a statement P implies a statement Q. If I cannot prove it, then I should prove that it might be sometimes easier to prove that the negation of Q implies negation of P. Means not P implies not Q. So if the thing is countable, then its subset is also countable. If a set is countable, a subset of that set is countable. So if the subset of a set is not countable, the set itself cannot be countable. So what we are going to show, which is a traditional thing in the literature, is to show that, that is what Cantor also showed, show that the interval zero one is not countable. I think he first didn't prove it with the diagonal, the method that we are going, much later he introduced it. But that's what it is. It's one of the most beautiful proofs in mathematics. Like many proofs in mathematics, one of the most important tricks of the mathematician is to prove by contradiction. That is, you tell that your statement is wrong. Whatever you want to prove is incorrect. So you start with the incorrect hypothesis and then show that there is some contradiction. So here we assume that let 0 and 1, this set, remember 0, 1 means 0 and 1 are excluded, is countable. So we are starting with this presumption. We are assuming that 0 and 1 is countable. So if 0, 1 and this interval is countable, what does it mean? So let us list the numbers. So they are countable, means I have been able to match them with the set of natural numbers. So I am matching them with say alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and so on. So they are all matched with a set of natural numbers. They must be because they are countable. So you can put a one-to-one correspondence between that set and the set of natural numbers, and hence now these are all numbers between 0 and 1. So the decimal expression would be 0 point something. That we have learned about the decimal expansion, and so you understand, and that's also a very basic school thing which you get used to. Sometimes you have to get used to things in mathematics, not thinking too much about it. So here is a story I want to tell that I tell sometimes in my classes, that once the famous 20th century great mathematician, the star mathematician John von Neumann, who is also responsible for many things for the development of the modern computer and modern economics, game theory. So he was once asked by one student couldn't solve a problem in the US. Actually, he couldn't solve a problem in physics. He was trying to solve a differential equation. So his supervisor told, why don't you go and talk to Professor von Neumann? So he could finally catch Professor von Neumann in a party dancing with a beautiful woman, and he goes and asks, so what shall I do with this problem? He said, use the method of characteristics. So he went and found out what is the method of characteristics, used it and solved this problem. But then next he calls up von Neumann and tells him that, but I couldn't really understand what is this method of characteristics. So he said that sometimes in mathematics you don't understand things, you just get used to them. So decimal expansion is something you don't, many people might not really understand why it is, you just get used to it. So here I can start with this decimal expansion, 0 point A1, A2, A3, A4, A5, A6. So these are numbers basically. And you know that decimal expansion can be either infinite, or if they are terminating, then they could be, if they are infinite, they are periodical, or they are terminating basically. So sorry, B1, B2, B3. So for things which is terminated, we can write 0, 0, 0, 0, 0, 0 as in places where suppose it's terminated B4, then 0, 0, 0, 0, whatever. So I'm doing B2. Cantor did a very novel thing. He said, come to A1, choose any number between 0 and, choose any number between 1 and 8. Choose any number between 1 and 8. That is not equal to A1, right? So you put down that number, whatever it is, say some K1, so 0 point some K1. So this goes. Now you come to B2, do the same thing, choose any number between 1 and 8 and which is different from B2 and put it there. And so you do for the rest. Do for this, do for that, and so and so forth. Now Mike, you might ask, why are you asking me to choose from 1 and 8? What is the possibility? Why 0 and 9? Suppose you take 0, 0, 0, 0, suppose none of these are 0 and you put 0, 0, 0, 0, 0, then you will get 0, and 0 and 1, 0 is not in that set. So basically you can't say anything. 0 doesn't belong to that set. So, but if you say take 9, so you have 0.99999, if you do that, you might just get 1. you would say take 4 and then this is 4 and then 9999999, you will get 0.5 which is already there. So, that sort of thing. So, you avoid generating a number here which is already present there, right. So, now you might ask me what about 1/3? 1/3 is what? 0.33333. So, suppose I start taking 333. But the problem is when you are just going down, essentially counting down, because you, so if you take, so when you are essentially counting down, so if you have 0.3333333, you cannot do that, because what we do, we have expressed everything, these are, because now these are all countable. So, we have expressed everything in the form of decimal. So, 1/3 here is also expressed in the form of a decimal. So, when you come to that 1/3, you have 333333333, immediately you will cancel 1 3 and put something else. So, that number cannot be repeated. So, what you have done, so this number cannot be the first number alpha 1 because it is not, first number is not same as A1. It cannot be the second number because the second number is not same as B2. K2 is not same as B2. It cannot be the third one because the third number K3 is not same as C3. It cannot be the fourth one because it is not the same as D4 and so forth. So, finally, we have created a number. By looking at the decimal expansion, it is a number between 0 and 1, but it is not in the list of numbers which are in one-to-one correspondence with the set of natural numbers. So, which means that I have not been able to put all the real numbers lying between 0 and 1 in one-to-one correspondence with the set of natural numbers, and thus proving one of the greatest conclusions in all mathematics, that the set of numbers, real numbers between 0 and 1 is not countable. And with this great result, it's called the Cantor's diagonal method, I would like to end the talk. There will be some more stuff in the notes which you can see when it will be uploaded. So, in the next class, we are going to talk more about irrational numbers. There's a bit amount of fun there. You can play a little bit with polynomials. So, for proving certain irrationality of some numbers, you have to use actually your knowledge about polynomials, and that is what we will see in the next class. So the whole idea about numbers would end there, and then we will go into doing the actual calculus, functions, limits and all these things. Thank you very much.